This is question 9 from paper 3-1 from the June 2020 exams from Cambridge International. Up the top right of this screen, a card will bring you to the playlist for all my solutions for this paper. And in the description below, you can find a link to an image of this question so you can try it before looking at my solution. In this question, they give us 3 vectors here, and they're going to ask us to solve a few questions about it. Now, you don't have to draw these vectors out, and I'm not going to be particularly good at it, but I'll give it a go as a little sketch. We'll say this is the x-axis, or I is in the x, j is in the y, and k is in the z-axis, although it doesn't really matter, you can change it around. So we'll go I being out this way. I won't bother writing them in. So 2i, and then k will come out this way. So we'll put one of our vectors here on the ground. This one's on the ground, as it were, in this picture. OB would go out 3, up 2, and then out 3 again. So this is in the air about here somewhere. I hope that sort of makes it clear where it is. That's on the ground in this picture. This one's in the air. And the last one comes out 1, goes up 1, and comes out 1. So it's here, and it's somewhere in the air around there. And we have a triangle between them. Now, you cannot see what angles those triangles are because it's in 3 dimensions. You'd have to do this in real life, look around it. And that's where these vectors come in so useful. Or more to the point, the scalar product comes in when we want to deal with these angles. So that's some of the power of having vectors. You don't have to draw this, you don't have to see it, just thought I'd point it out. Part A asks us, using the scalar product, show that the angle ABC, let's see, this was A, was it? This was B, and this was C. I hope that's C. I think that's correct. And so they want to find out what this angle in here, or show that this angle in here is a right angle. Now, it looks a little like a right angle in our picture, but we're going to use maths. No picture, just use maths to find that out. Another thing I'm going to change is how we write this. I just want to save myself a lot of writing. Instead, we're going to, I'll rub this out here, and because I'm not going to use these IJs and Ks. You can, it's fine. It's no different than what I'm about to do, except it's just a little bit faster and shorter. Another way to write it would be 2, 0, and 5. That's the vector, so 2i, 0 j's, and 5 k's. This one, I don't have quite enough room, so apologise if it's small. It's 3, 2, and 3, and this last one here is 1, 1, and 1. 1, 1, and 1. So I'm going to use these vectors rather than the IJs and Ks. It's just quicker to write. So using the scalar product, show that the angle ABC is a right angle. Now, to show that, I'll draw a triangle again. This time, I'll pretend we can move around and look at just from the side. So we'll say A, B, and C. Different letters. Well, let's change it so it looks a bit more like this one. A and C. Although it really doesn't matter. This is just to help us think about it. Now, how we talk about this angle, we want to talk about this angle in here. So we want the vectors BC and BA. These vectors they give us are all coming from some O over here. This is O going to B, O going to A, O going to C. What I really need here is B going to C. I want that vector. And also I would like the vector, well, I'll write it in a moment, B going to A. So let's try and find that. There's probably a bit, it'll be fine. So how do we get the vector B going to C? Vectors are quite easy to find. This vector, this vector going from B, let's put O in over here, from B to C is identical as this vector. B to A to O, O to C. This vector is identical to this one. Because in vectors, it doesn't matter the path we take. All that matters is where do we start and where do we end. So this plus this would be the same. So let's use that as an idea, although I went too many there. So B to C. The quickest way I could get there would be probably B to O, O to C. So let's write that in. B to O plus O to C. That's another way to write BC. And here's the great thing, I actually have both of these up here. I'll get rid of the picture for now on just because it's a bit in my way. Because this is not quite this. B to O, I have O to B. Well, good thing, B to O is the same as minus O to B. So O to B plus O to C. Or another way to write that would be O to C minus O to B. And that's the common way we usually write it. Often students will skip straight to this bit because it comes up so often. And similarly then for, I guess I do need my picture here, B and C and A. Similarly for B to A, I'll skip straight to the answer. It's OA minus OB. And we can put that into these vector forms. It's OC, this one, minus this one. So it's just 1 minus 3, minus 2. It's just 1 minus 2, minus 1. And it's just 1 minus 3 is minus 2. This one down here is A minus B. Here's this one's A, so it's 2 minus 3. That's minus 1. It's 0 minus 2. It's minus 2. And it's 5 minus 3. That's plus 2. There are those two vectors. So once we have these vectors, this is, just to make this a bit clearer, this is BC and this is BA. Once we have these vectors here, BC and BA, if we get the scalar product of two vectors that are going like this, we talk about the angle in here. We find lots of information about the angle. We have a formula in our formula tables when we go into an exam that the dot product of let's say A dot B is equal to the length of A times the length of B multiplied by cosine of the angle in between. So let's do that with these two vectors. Again, I'm going to rub my little picture out and I'll squeeze this up here. BC dot BA will equal like I said, the length of them equal the length multiplied by the length times cosine of the angle. But here's the thing, the angle, they're asking us to show that the angle is 90. Cosine of 90 is 0. So they're really just asking to find, is this 0? So let's just find out. We get minus 2 minus 1 minus 2 dot minus 1 minus 2 plus 2. And what does that equal? The dot product tells us just the first times the first. Minus 2 multiplied by minus 1 is plus 2. Then add on the second times the second. That is another 2. And then add on the fourth one. So plus minus 2 times plus 2 is minus 4. So if we add these up, 2 plus 2 minus 4 is of course the 0. And you could just write something along the lines of therefore perpendicular. You wouldn't even have to write English. You can write that in English if you want, but that just means therefore perpendicular. And you're going to get full marks for part A. Now part B asks us to show that the triangle ABC, there it is in there, is isosceles. I'm going to once again, you know what, let me rub all over here out, and I think I can finish this question over here if I just write in B, C and A, I think it was. So we found out that this is a right angle here. B, C and A, I think. If I got that mixed up, it doesn't really matter. So we want to find out, is this isosceles? There's two ways to do that. We could find out that this angle is equal to this angle. You can do that. You'd have to get we have this vector, we have this vector. You'd have to find this vector, use the dot product to find this angle, use the dot product to find this angle. If they're equal, that's brilliant. But there's an easier way. How about we find that this length is equal to this length? Because here's the thing, we already have this vector. We already have this vector. Once you have a vector, you understand the length and the angle quite well, or well, the angle between two vectors. So let's just find the length of this vector. BC is this one here. The length of BC, let's put it here. The length of BC is equal to minus 2 squared plus minus 1 squared plus minus 2 squared the square root. Now, if you don't believe that, you can just draw out a three-dimensional one and work out the three-dimensional triangle and get the length of it by using Pythagoras twice. What I mean by that is we get the shadow down and you get a triangle down the bottom here. That's a right angle. You work out the length of this, then you work out the length of that. Anyway, you would have done it in class. It's given to you in the exam, this formula. It's quite easy to find. So this is 4 plus 1 plus 4 is equal to 9, square root of 9, which is equal to 3. And then the length of BA, it should be quite, we can already see it's the same because it's 2 squared, and 1 squared. 2 squared, 2 squared, and 1 squared. So that's equal to, well, let me write it that way, 1 plus 4 plus 4 square root is equal to square root 9, which is equal to 3. Therefore, they're equal. Therefore, isosceles. That's enough as well. The exam doesn't need much English. They just want you to tell them your conclusions. Now, for part C, it's a bit more complicated, so I'm going to just rub all this out, and I'll leave this picture here, and we'll put, say, O over here somewhere. And actually, we'll draw a more simple picture. But it wants us to find the length of a perpendicular line from O. There's a couple of ways to do it. A long way, I'm going to show you the easier way using vectors, as you are intended to do in this question. So I'll just rub this out, I'll be back in a moment. Okay, like I said, part C asks us to find the exact length, that's important, the exact length between O and the line through BC. So that's not just BC, that's the line, could go anywhere here. So the way I've drawn it, it looks like it's about here, but no, it could be, O maybe it's over here, and it could hit off this imaginary line here. Apologies for the noise in the background, there's nothing I can really do about it. I think I'll just finish this question. Right, how to do this question without using vectors, we do understand what this point is. OB is 3, 2, 3. This point here, C, is 1, 1, 1. You could use classical coordinate geometry, but it gets a bit difficult in 3 dimensions. You'd have to work pretty hard at it. But you could do it, but I'm not going to show you how to do it because it seems a bit pointless to me. And we're going to use vectors. So using vectors, we are going to define every point on this line. So that's the first thing I'm going to do. So any point or any vector to a point on this line, let's say. So O going to this point, the vector O going to this point, the vector O going to here, the vector going anywhere, we'll call it OR, although you can call it anything you want, is equal to, all I need is any point on this line. I'll go ahead and pick this one here, or any vector. So OB I'll go ahead and pick. So 3, 2, 3. And then all I need to do, once I have a point, I can get anywhere on this line if I just move in a direction on the line. And I understand the direction on the line. I understand BC. I have a vector for BC. So if I just move like a half of BC, I'll get here. If I move a third, I'll get here. If I move minus 1 of BC, I'll get up here. If I move 2 BCs, I'll get down here. I can get anywhere on this line by using BCs. Minus 2, minus 1, minus 2. All I have to do is move a certain amount along it. Maybe a half, maybe 1, maybe 8, maybe 7.342. Some number. Now, by convention, we just use lambda, but honestly, use any letter you want. Students hate using this. I just got used to it over the years. It often means wavelength as well, but we often use it for this. So I'm just going to go ahead and use it. You'll see it in books, you'll see it in the exam papers a lot. But again, any letter you want is fine. Now, this vector will go from 0 to any point you want on this line. So that's really powerful. But we can write this a little bit better than this because a scalar multiplied by a vector is just the same as, well, let me do it slowly here. 3, 2, 3. A scalar multiplied by a vector would just work like this: minus 2 lambda, minus lambda, minus 2 lambda. Once you deal with 2's and lambdas, it does look confusing. So maybe I should have used a different letter. And you can just add vectors quite easily as well. So this is just 3 minus 2 lambda, 2 minus lambda, and 3 minus 2 lambda. That's just one vector. So this is, let's call this point here something P. This is just O going to P. I don't know where P is, by the way. Remember, it could have been down here. I'm just drawing the picture to help emphasize it. But this is a vector going from O to anywhere on P. And that's what the question wanted. They wanted a line going from, they want the length of it ultimately. They wanted a line going from O to this line. That's one instruction they gave us. So we've completed that one instruction, one of those instructions, that this O goes to somewhere on this line. The next thing they want us to do is make sure that it's a right angle. So we just seen how to make sure of right angles when we're dealing with vectors. We have OP, and we also know a vector, any vector really going here, that's BC would work. BC is equal to minus 2, minus 1, minus 2. If we just get the dot product of these, we'll find out what number lambda is. Because remember, lambda is every number. Like lambda being 0 would look like just this. Lambda being 1 would look like this. Lambda being minus 1 would look like this. Lambda being a half would look, well, I'm not sure what P will look like. I'm just going to cheat and look ahead. Actually, it turns out P is over here somewhere, and just off to the right. Right, so let's do that. Let's get the dot product between OP and BC. The dot product is equal, well, let's do it underneath it, I think. The dot product is equal to this multiplied by this. So that's minus 6, minus 2 times minus 2 lambda plus 4 lambda. Then we get minus 2 plus lambda. Then we get minus 6 plus 4 lambda. And we clean all that up. Minus 6, minus 6, minus 2 is minus 14. The lambdas is plus 9 lambda. And we know that all equals 0. We know that's going to equal 0 because it's a right angle. We're finding out which lambda makes it equal 0. We just rearrange this. We get 9 lambda equals 14. We get lambda is equal to 14 over 9. So 40, that's like 1.5. So remember that was 0, that was 1. So that's how I knew we're somewhere over here. I just looked at my answer from earlier. We're not finished. So many students finished there. They're not looking for this. We're actually looking for OP, or the length of OP. So we now know what lambda is. So let's put it back in here. I'll go ahead and cheat and use my answers, because I just put this in a calculator. I just put 3 minus 2 multiplied by 14 over 9. It'll do the fractions for me. So I get OP is equal to 1 over 9 multiplied by minus 1, 4, minus 1. So that's what I get OP to equal to. And I still need to find out what the length of OP is. Let's see. So to get the length, we just get this one squared. Remember, it's multiplied by this. So we better multiply by this squared as well. And we get this squared plus this squared plus this squared. I'm running a little out of space here, so you'll have to forgive. Oh, well, I guess we can see it in our heads here. It's going to be 1 plus 16 plus 1, that's 18, divided by this squared, that's 81. So 18, or the square root, well, yeah, let me write it in this way. Square root of 18 over 81. But we can make that a little neater. Let's see, 9 goes into both of them. 9 goes into this 9 times square root of 9 is 3. Yeah, we can do this in our heads. This is square root of 2 divided by 3. But let a calculator do that if you're not so happy with it. Most calculators nowadays will give you the exact answer. And that's what they want, the exact answer. They don't want the decimal places the calculator might give you. You need to give them this part. One thing to point out here is I used the vector BC. I didn't have to. I could have also used the vector CB. But I had BC from earlier on. I could have used half of BC. I could have used a quarter of BC. I could have got the unit vector from BC. It doesn't matter. All I needed was any vector going in this world, in this lines world. Could go this way or this way, I don't care. You would get different lambdas out than I did if you used different vectors here. Which did I use? BC. There was BC here. If you used a different vector at this part, you would get different lambdas, or maybe use different letters as well. Okay, if you have any questions about that, vectors give students lots of troubles, but they're so useful. If you're going on to do so many college level things, especially engineering, science, physics, you're going to use vectors because they're so useful. They're so much better to use a vector than coordinate geometry once we get to 3 dimensions, because 3 dimensions is just too hard for coordinate geometry. But with vectors we can use 3, 4, 5, 20. We can use n number of dimensions a lot easier. It gets hard, sure, the higher dimensions we go, but it's a lot easier than doing coordinate geometry. Okay, thanks for watching. Have a great day.